In this video, I'll briefly go over each level available in the BAT folder of the content examples for my GameTools Blender extension. Each folder includes a source directory containing the blend file, the mesh, an XML report, and textures. The blend file is particularly useful as it shows the exact settings used for baking and how the BAT bake tool was configured to achieve the demonstrated result. The first folder demonstrates the continuous packing mode. This is the same feature showcased with the VAT and OAT tools, so I won't go into too much detail here. It simply shows an experimental method for packing data into textures when there are either too many bone transforms to fit per frame, given the maximum texture width, or too few if a specific texture width is enforced. The second example is quite interesting and demonstrates the ability to bake a bone's custom property. This opens up a lot of creative possibilities. You just need to add a custom property to a bone, animate it however you like, and bake it. It can then be assembled just like any other transform. Pretty cool. The next example shows how to customize the reference pose. By default, it's the first frame of the animation, but you can use something like a T-pose clip instead and exclude that clip from the bake. This does not change much by itself, but it's probably more useful when using the retarget feature. More on that in a moment. The following example demonstrates baking bone transforms every nth frame. Not much to say here, but keep in mind you may need to adjust the playback frame rate to account for having fewer frames describing an animation of the same length, if that makes sense. The next one, actually I'll highlight this first, demonstrates the retargeting feature. I already covered this in 2 previous videos, so I'll skip the explanation. In short, just create a custom property on the high-res mesh of type datablock named bakeTarget and point it to the low-res mesh. Then provide a T-pose clip for binding and exclude it from the bake, and that's it. And multiple high-res meshes can also target multiple low-res meshes as shown in this example. The animation was originally performed on spheres and then baked onto low-res cubes. Next up, this example is nearly identical to one found in the VAT folder. Like I mentioned in a previous video, I'll likely make a dedicated video about this Niagara system. It creates a state machine to randomly play certain clips. Very interesting. Next example, nothing fancy here. As the tooltip says, it's just a test to double check that normals are properly fixed. The following is a textbook example of bone animation textures, using a position texture and a rotation texture with axis angle encoding, like demonstrated in the first BAT video. Here it's the same concept, but both the position and rotation textures are remapped to the 0-1 range for storage in 8-bit RGBA textures. This reduces memory usage at the cost of animation fidelity, though the loss in quality might not even be noticeable. You just need to provide the offset and range values reported by the bake tool. This next one is a crash test for baking bone scale along with position and rotation. Applying scale can be a bit tricky, but this template function demonstrates one possible approach. The next example shows how to use 3 axes to encode the forward, right and up vectors of each bone. This lets you apply rotation without trigonometry. It's likely more expensive though due to the additional texture fetches, though you could potentially bake just 2 axes and derive the third. There are many things to try. This just demonstrates another way of baking bone rotation. Axis angle encoding is generally preferred. A similar idea is shown here, but with rotation expressed as a quaternion instead of axis angle. Same concept, different format. This method was also shown in the OAT content examples. The rotation, stored as a quaternion, can be bit-packed into a single 32-bit float, allowing both offset and rotation to be stored in a single 32-bit texture. This reduces the number of texture samples needed. While the offset probably doesn't benefit from 32 bits, 16 bits is often enough, it's still an option worth exploring. The next example features an animation with very few keyframes, used to crash test quaternion spherical interpolation between frames. That one was already covered earlier. The next example showcases one of the advantages of using forward, right and up axis to represent rotation. It can also represent scale. This one demonstrates the stack offset mode for baking when there are too many bones for the maximum texture width. It allows for pixel interpolation between frames, assuming the data can be interpolated, like position, for example. A similar principle applies here. This example demonstrates the stack adjacent mode, also for handling too many bones. This method does not support pixel interpolation but has simpler sampling logic. More details can be found in previous videos and in the wiki. This example is particularly interesting. It shows bone indices baked into vertex color. This reduces the size of the skinning texture by half, but it only works if the total number of deforming bones is 256 or fewer. The next example builds on that idea. Only the two most influential bones are considered, with both their indices and weights baked into vertex colors. This removes the need to sample the skinning texture entirely, meaning the mesh doesn't require a UV map for it, potentially avoiding the need for 32-bit UVs. It's definitely worth experimenting with. Again, this is only possible if the number of deforming bones stays under 256. And that's it for the content examples related to bone animation textures. The wiki should provide more information if anything remains unclear.